Hello, everyone. Welcome you back to study robotics course. Today we move on to study module 2. And today we are going to study the lecture 1 of module 2. Before we enter the study of lecture 1 in module 2, it is always good to remind you about the learning objective. The learning objective of this course is for you to become a designer of a robot as a product. By now, you should know there are many potential users in manufacturing, in society, in transportation, in medical field, etc. Okay, so these potential user of a robot have the generalized need, which is to have a motion provider. Therefore, robots are very good candidate to serve as a motion provider. Therefore, the focus of your study should be on the answer to question number 3, question number 4. All right, so you should know, okay, what will be your robot which could meet the generalized need of the potential user in manufacturing, in society, and you must study the solution behind the design of your future robot. All right. Then for the generic answer to question number 3, this slide, okay, show you the guideline. So inside the blueprint of your robot, you should be able to see the presence of a module 1, presence of a module 2, presence of a module 4, and also the presence of module 3, which is about robot modeling in terms of kinematics and dynamics. All right, and this slide basically show you knowledge flow and signal flow, and behind the signal flow there must be energy flow. All right, so today we move on to study the design of a robot's body. Then from the viewpoint of a designer of any mechatronic product, we may talk about the material flow, energy flow, signal flow. Okay, then for robot, we must add in one extra flow, which is knowledge flow. Okay, so in module 1, basically we have studied the knowledge flow inside a robot, and the input to this module are the job description, and the output from this module are the motion description in terms of time function of motion equation. All right, so then you see, okay, the purpose of module 1 is for you to design robot software which could handle knowledge flow. Okay, then the output from module 1 must be physically executed or performed by the mechanic system of your robot. So therefore, module 2 will help you to study the knowledge, okay, which will enable you to design robot's body. All right, and then the knowledge behind this blueprint, okay, include all these topics which has been categorized into 4 modules. So by now you have already completed the study of module 1, and the key takeaway from the study of module 1 is for you to be resourceful enough to design robots software, all right? And this software basically handle knowledge flow inside your robot, all right? Then we want to know, okay, how to let robot to perform motion, which will be the output from module 1. So the answer is to design robot's body, which will be able to perform required motion. And this will be the focus of a study for module 2. And today we will study lecture 1 of module 2. Okay, so in order to prepare you to put yourself into the mindset of designer, so I give you this extra 5 questions. So this will help you to focus your study on the design of a robot's body. Okay, so once you are going to engage in the project of designing robot's body, systematically you should be able to answer these 5 questions. Question number 1, what is the energy flow inside the body of your robot? What is the signal flow inside your robot? What is the knowledge flow inside your robot? And in particular, what is the relationship between energy flow and the signal flow? So the answer to question number 4 will be taught to you, okay, in module 3, because module 3 basically is to answer this question: what is the relationship between energy flow and the signal flow? Okay, for question number 5, you need to know what is the relationship between signal flow and the knowledge flow. So actually, module 1 has already taught you about the answer to question number 5, all right? Because in module 1, input is a job description in the form of a human language, okay? And the output is the motion description in the form of trajectory equation. And this equation could be implemented inside the library function or script commands. So therefore, you see the relationship, okay, between knowledge and motion signal, all right? So basically, module 1 has already taught you about the relationship between signal flow and knowledge flow, okay? So now we, okay, focus our study on module 2, which is to design robot's body. In this way, the robot should be able to physically perform intended motion, all right? So for the first lecture in module 2, we need to answer this question, because once you put yourself into the mindset of a designer of a robot's body, then you may want to know, okay, what are the details for you to undertake the design of a robot's body, okay? So in order to better understand the answer to this question, it is good to adopt the viewpoint of a system, because a robot is a complex system which include many subsystems. Therefore, we need to design each individual subsystem. So in this way, then you will have a better idea about the detail of designing a robot's body, all right? So we start with the general concept of a system, then we zoom in to the detail of a robot system, okay? Then once we know what should be the system inside the robot, then immediately you know, okay, what should be the design scope for the design of a robot's body, all right? So in general, a system is a set of entities which are interconnected together and add together for achieving common goal or outcome. For example, this robot has a leg system, has an arm system, has a power system, has a control system, has a perception system, okay? So they are all embedded inside the body of this robot. So they work together in order to achieve this very impressive okay, outcome of behavior, all right? So now we can ask you, start to think about the, let's say, 5 systems that are familiar to you, okay? So as a student, immediately you know there is an educational system, and there must be a transportation system. Otherwise, when you come to the campus of university, you have to, okay, to come by foot or by feet, okay, by walking, if there is no transportation system, all right? So inside the campus, we may have a power system, okay? And we have an electronic system. We also have an IT system to manage the information about the student and the faculty member, etc. Then we also have a research lab, teaching lab, and inside the lab, you may see many other systems, such as a robot system and the vehicle system, etc. All right, so it should be quite easier for you to name 5 systems which are familiar to you. All right. Then, based on this example of a system which are familiar to you, then you should be able to understand. For every system, there must be an input. For every system, there must be output. For every system, there must be inner process which produce output from the input. So in technical term, so it means the system has an input, system has a response, the system has a transfer function. All right. And if we look at the relationship between input and the output, then system could be classified into 2 types. One is an open loop system. Open loop system is a system that the response depends on the input and the response are not equal to the input. Okay, so for open loop system, the input could be let's say mechanical energy, then output could be electric energy, etc. Okay, so output is not exactly equal to the input. Okay, and then okay, so in this case you have an open loop system. Okay, then for closed loop system, so this is different from open loop system. Okay, for closed loop system, then the output is equal to input, because with this negative feedback loop, the controller will make this error to be 0. When this one is 0, so it means what? Input minus output equal to 0, then output equal to input. So this is a very special type of system. Okay, then in our society, in industry, all the system, almost the majority of the system behave like a closed loop system. Even for human body, okay, our brain control our arm, control our body, control our leg. Okay, so all this interaction among our eye, our brain, our finger, our arm, our body, our leg, okay, belongs to the behavior of a closed loop system. Okay, so human being is a typical example of a closed loop system. All right, so it's quite straightforward. Okay, then regardless whether you face a open loop system or closed loop system, and both of them must produce output, then we can divide the output from any system into 2 categories. One is called as a transient response, and the second one is a steady state response. Okay, so first we need to understand what is a steady state response. A steady state response means the output which stabilize at the steady state. Okay, steady state means there's no change of the state. All right, so once you understand what is a steady state, then immediately you understand what is a transient response. Transient response means the response of the output which goes from one steady state to another state. Okay, so in other words, it means the response between two adjacent steady state. All right, so this is the meaning of a transient response. All right, and this slide show you some typical example. For example, here this is a previous steady state, and this one is a new steady state. Okay, then the actual output will take time, have this kinds of behavior before it converge to the new steady state. Okay, and for this example, it's like this. Okay, initial steady state, okay, is at this point. Then the new steady state should be here. Then you see the actual output will take time, okay, before it will reach the new steady state. All right, so this slide help you to understand the relationship between steady state and the transient response. All right. Then once a system has a transient response, then we would like to know the performance, because in practice, we do not want to see the transient response, because all these output are useless, okay, in industry and in society. So all these are unwanted response, because we just want to have this steady state and the new steady state, all right? And the response in between is meaningless to us. So therefore, we must minimize the transient response. Then how to indicate the level of reduction of a transient response? Then we need to come out some criteria. First one is the stability. Second one is about response time. And the third one is about the response accuracy. And this slide illustrates the stability. So for example, if we want to make the output to move from current steady state to the new steady state, okay? So this is a requirement. And if the output from the machine, from robot behave like this, then the actual output will go to infinity, or like this, after zigzag, then it goes, or after oscillation, it goes to infinity. So this is a typical scenario of instability. So system will not stable, okay? If system behave like this, then you'll see it takes time for it to reach the new steady state. So it takes time for it to reach new steady state, okay? Then for this one, it will never go to infinity, but it never converge to the new steady state, okay? So you cannot name this one unstable. You can also not name this one as a stable. So therefore, we give this name. We call it as a marginally stable. Okay, this is the oscillation. Okay, continuous oscillation. Okay, so this is the idea about the stability. Then response time. So it means if the time taken by the output, okay, for it to enter an error band, for example, plus minus 10%. Okay, let's say we can tolerate plus minus 10% error. So then the time taken by the output to enter the error band. Okay, so we call this as a response time or settling time. So actually, you may have another indicator about the response time. This is called as a rise time. Okay, so time taken for the output to change from 10% of a new steady state to reach 90% of the new steady state. Okay, this is the rise time. So this is the time taken for the output, okay, for it to change from 10% of the final value to 90% of the final value. All right. So if let's say we change again the new steady state, okay, so this is the new steady state, initial steady state, then this is the new steady state, then we change the new steady state back to the initial one again, then the actual output will respond in this way. All right, so this is the response time. Response accuracy is to see whether the actual output will equal to the new steady state or not. If not, then there's an error. Then we can calculate the percentage of error. That gives us indication about the response accuracy. Ideally, we want to achieve 100% accuracy. All right. So that's the concept about the system in general. So basically, system has an input, has an output, has a relationship, a function which link input to the output. And we may have an open loop system, and we may have a closed loop system. And in general, the output include transient response, steady state response, and we want to minimize the transient response or reduce the transient response, okay? And then we need to have some indicator about the stability of the response, accuracy response, and the time of the response, okay? Then the design objective actually is to achieve 100% stability, very fast response, and 100% accuracy. All right. So with these three indicators, then we can, okay, set some specification. All right. So now we apply this concept to the case of a robot. Okay. So robot actually is also a system or complex system. Okay. This is because inside a robot, we have many modules, many rigid body, which are connected together and add together. Okay. For the purpose of achieving some goal. And the generic goal should be try to approach human-like skill and try to approach human-like intelligence, because the robot can use a human being as a reference, okay? Try to outperform a human being in terms of skill, in terms of intelligence, all right? So now I'm going to show you some typical example of a robot system in manufacturing. And here you see we have a system which consists of a mechanical system of a robot. In this case, it's a robotic arm plus a control system of robot. You see, this looks like a robot's brain. And you may also have the tool system for welding, etc. Then you may also have the system for the workspace. So you see the workspace is also a system which has a certain degree of freedom. All right. So you must have okay, a system viewpoint about the robot. Okay. So you should not say robot it just refers to this robotic arm. So actually a robotic arm is just one subsystem inside robot overall system. All right. And this is a second example. So in this case, you may have this CNC machine. Then you see you have a brain of the robot. Then you have the arm of the robot plus the tool, okay, mounted on top of the robot, etc. So these form a complex system, okay. And one more example. Then you see we have the body of the robot plus the brain of the robot, okay. And then you have a display system, etc. And also you have the complicated hand for the robot. Okay, the hand system of the robot, arm system for the robot, etc. All right. And in this case, instead of a single robotic arm, now we have a two robotic arm plus 3 eye for the robot. Then we have a two controller, two brain. Okay, so this form even more complex system for robot. All right. So since robot is a system, then we can talk about what should be the input to robot. From the study in module 1, then you understand, okay, at the highest level, the input should be job description, and the job description could be decomposed into task description. Task description could be decomposed into action description, and the action description could be decomposed into motion description. And the motion description could be described in terms of equation. And the inside equation, we have a variable, and the variable carries a value. All this value correspond to signal, okay? Then behind the signal, there must be energy associated with the signal. For example, the torque and the angular velocity. If you time these two together, it refers to mechanical power, okay? So that is energy, all right? So behind signal, there must be energy, all right? Then the response from a robot system should be similar to the case of input. The reason is because we use a closed loop feedback control system to implement robot system. Now let you remember for closed loop control system, output is equal to input. Therefore, if the input is task description, then output should be the perform the task or accomplish the task. Okay. If the input is action description, then the output should be perform the action or accomplish the action, etc. All right. So they are symmetric because inside a robot system, we always make use of closed loop control. Okay, to design a robot control system. All right. Then so in general, okay. So now you understand. A robot system will normally include many subsystems. Okay, so use this as an example. This robot must take energy as an input. Therefore, so there must be a power system, because without the power, without energy, there is no signal. Without the signal, there is no motion. Without the motion, there is no action. Without the action, there is no task. Without the task, the robot cannot perform any job. All right, then the input side is empty, then output side will be empty. Okay, so energy is a necessary input. Okay, inside robot system. Therefore, we must have a power supply system. All right, so this is a necessary one. Then besides that, a robot must have a physical body. Okay, in order to move the tool. Okay, in the workspace. Therefore, robot must have a mechanic system, and the motion to be performed by mechanic system of the robot must be under control. So robot must perform a controllable motion. Therefore, control system must be there. All right, and since inside the robotic arm you may have many device and many other subsystems, then all these systems must be able to communicate. Okay. On the other hand, if you deploy more than one robot to work together, then between these two robots, there must be a possibility or capability for them to talk to each other or exchange the data, etc. All right, and lastly, this robot arm must be able to interact with a human being, John, because robot must be able to receive instruction from human operator in order to know what to do. All right, so programming system is necessary. Okay, so this is the way for us to instruct, okay, robot, okay, what to do. All right, and then for advanced robot system, eventually we may incorporate vision system. In this case, you see you have a 3 camera there, and also it is good to incorporate speech system. Then in this case, we can let robot to learn our language. Then in future, we can use human language to instruct robot to do the intended task. All right. So these are the typical subsystem inside a robot system. All right. Now we try to zoom into the detail of a mechanic system, control system, programming system, because these 3 are the major one. And the power system, basically we just use existing power supply from the factory, or use a battery to provide the power supply to the mobile robot. Okay, so because as a designer, you understand there's a general guideline. The general guideline is to not to invent the view. Okay, if there's an off-shelf item or system, so we just purchase the standard item or standard device, standard part from the market. Okay, in this way, there's no need for us to reinvent the view, because otherwise it will be costly for the product. Okay, so therefore, because today in many locations, there are many standard systems which could play the role of a power supply. Therefore, then this should not be our focus. Okay. But however, different robot may have a different mechanism, appearance, etc. So this should be our focus of a study, and the control system, okay, should also be the focus of our study. And we also need to pay attention, okay, what should be the standard module for us to use, okay, in terms of operating system, programming language, okay, and the library function, okay, which are available in the market. So therefore, we use existing module from the market, okay, or existing software module, okay, in the market, okay. Then for this one, so depends the hardware for robots brand, okay, then we need to know how to operate the input output module inside the robots brand, all right? So now we just focus on the major or the key subsystem inside the robot, and obviously mechanic system is the #1 key system inside the robot, okay? But conceptually, the mechanic system of a robot consists of appearance, mechanism, and the structure. And among these three items, mechanism is the most important one, okay? And the mechanism actually is not complicated because any mechanism inside the robot consists of two basic building blocks. One is link and second one is joint, okay? So here we just show you example. Then graphically, we can use a cylinder to represent pivoting joint, and this graphic symbol to represent prismatic joint, okay? Then for this design solution, so you will see we have one pivoting joint followed by prismatic joint, then another pivoting joint, another pivoting joint, all right? So you have a 1, 2, 3, 4. So this robot has a 4 joint, okay? So therefore, this robot has a 4 degrees of freedom, right? So then this video show you, okay? So this video show you the mechanism inside this popular, okay, robotic arm, okay? Okay, so this is a very good video which gives you a very good overview about the design requirement of a new robot. In case if let's say you will be engaged in a design project to design a new robot, then okay, this video basically show you the design requirement. All right, and if let's say you want to study example of robot which has been designed by others. So again, this video also show you a good example, okay, of a design solution achieved by others. Okay, so this is a very, very good video for you to learn. Okay, and then you should have a rough idea about the requirement of designing robot. All right. So in the video, you have seen that this type of a robot usually has 6 axes of rotation, and each axis is driven by one motor. Okay, and each axis is a rotational axis. Okay, and then for this example, we have one extra because actually this robot has 7 axes of rotation, and the convention in robotics is to use a cylinder to indicate the axis of rotation, and another convention in robotics is to use z-axis, okay, to represent the axis of rotation. Okay, and behind that we have another convention in robotics. So in robotics, for every rigid body, we always assign a local coordinate system to it. So once you have 6 axes of rotation, so it means you have a 6 link. If you have a 7 axes of rotation, so it means you have a 7 link. Link is a rigid body. So therefore, we must assign local coordinate system to every link. Okay, so then, but later on we'll come back to this convention, I guess in lecture 3, when we study robots, the design of a robot mechanism. Okay, so by now you just keep this background knowledge in mind, should be good enough. That means for every link, there's a local coordinate system, and then we use the z-axis of the local coordinate system to indicate the axis of rotation provided by the joint or by the motor. All right. Okay. So then this is the example, and then you will see the Z7, Z6, Z5, etc. All right. So this is a example, okay, about the graphic representation of robot's mechanism, and in particular the degree of freedom. All right. Then this is also a popular robot in electronic industry. So we call this scalar robot, okay? Because this robot has 2 horizontal links which can move, okay? Can only move in the horizontal plane. And this robot has a vertical link which can undergo linear motion in the vertical direction. And the last one, the last link, eventually could undertake rotational motion about this vertical axis. So the graphic representation of this type of a scalar robot is like this. So the first joint is a pivoting joint. Okay, so this is a joint 1, then this is the link 1. So you will see joint 1 is mounted on the you can say you have a link 0 or base link. Base link is a base of the robot. This is a base link. Then link 1, link 2, link 3, then link 4. Okay. So then for this one you have so this is a joint 2. So this is a second joint. Okay. Then this is a joint 3, prismatic joint. Then joint 4 is a revolute joint. Okay. So this is a graphic representation of a robot's mechanism, because mechanism are the linkage which permit motion or permit the relative motion between 2 adjacent links. Okay, so this is different from a structure. Structure means is a linkage, is a static linkage. Okay, in which there's a restriction of a relative motion between any pair of 2 adjacent links. So that is a structure, because we do not want the structure to move, all right? But for mechanism, so it's different. So mechanism is a linkage, okay? But in which, okay, we allow relative motion between any pair of 2 linkage, all right? So that's about the key component in robot mechanism. So the key component in robot mechanism are the the mechanism or in robots mechanic system or the mechanism, because inside robots mechanical system, they are appearance, mechanism, and structure. Okay, so mechanism are the key component inside robots mechanic system. All right. Now we zoom into the key component inside robots control system. So therefore, this is the example showing you the control system, which could be coupled with the robot's mechanic system. Because for this robot, you have you say you have a John 1, John 2, John 3 is here, and the John 4. All right, so you have a 4 degree of freedom. So therefore, so at least the control system must provide the capability to control John 1, John 2, and eventually this may be the John 3 and the John 4. Then you may have an additional one for the control of the hand. Okay, you may have a gripper here. Okay, so then in this case, so you must have a capability that the control system must have this capability of controlling 5 axes. Okay, the last one is for the hand, control the degree of freedom of the hand. Okay, the arm manipulator itself has a 4 degree of freedom. Okay, then you can see what should be the key component inside a robot control system. Number 1 is what? Motor. Number 2 is what? Controller. Number 3 is what? Sensor. There's no indication of a sensor. So actually, the number 3 should be sensor. Okay, because you need to have a sensory feedback. Okay, so when you see this servo motor, so actually it means inside the motor there is a built-in velocity sensor. All right, so that is the case when you buy a DC motor. The optical encoder is included. Okay, so the 3 basic items inside robot control system are motor, controller, and sensor. All right, so it's like in the case of robot's mechanic system, you have an appearance, mechanism, structure. Then here, then you have a controller, motor, sensor. All right, and normally one controller should be able to control multiple motor. All right, and another feature from a controller is the capability to do communication, because normally all the microcontroller support serial communication, parallel communication, etc. All right, so this basically you can treat as a brain of a robot. All right, then the third important subsystem inside the robot should be the programming system, because once you have a microcontroller, then user should be able to write the program and in this way to instruct the robot, okay, to do intended task, intended motion, intended action, etc. All right, and for advanced programming system, eventually you can implement the digital twin of your robot. Okay, for example, this is a digital twin of a scalar robot. Okay, and this could be the digital twin of a human operator. All right, so you see this is a simulation done by our student in year 2003. So now you understand that the concept of a digital twin is not new, because in robotics we have already make use of this concept to implement digital twin of a robotic arm, digital twin of a human being. All right. So that means this is a simulation is a very, very important tool which allow us to implement the scenario, different scenario of a performing task, different scenario of a performing action, different scenario of a performing motion in a virtual space. Okay, and without the risk of damaging the physical robot or cause accident or injury to the physical human being. All right. So you understand. So this is a quite important and useful component inside programming system. So on top of that, obviously you need to have an operating system in general, okay, and programming language. So again, you see, you can identify 3 key components inside a robot's programming language. They are operating system, programming language, and the simulation tool. Okay, so if you follow the guideline, okay, in industry for designer, then the practice is to try to use off-the-shelf item, component, device, or system, or tool, etc. And therefore, immediately you understand, okay? So the job for robots designer should be quite straightforward because there are many existing operating systems. There are many existing programming language. There are many existing simulation tools. So therefore, you see, your job as a designer of a robot is not so heavy because you can just use or choose the off-the-shelf item, component, device, module, etc. All right. So these are the 3 key system or key subsystem inside your robot, and for each subsystem there are 3 key components. Okay, so then among all these key components, you can leverage on the available module, available standard items, standard system in the market. Okay, then in this way you should be able to lighten your design job. Okay, so by now you have a rough idea about what to design. Okay, since this is the first lecture in module 2, and the key takeaway from this lecture 1 is for you to know what to design, and immediately you understand. Okay, so majority of the design work should be focused on the mechanic system design, control system design, then integration with the programming system. Okay, so then in this way you can put all these 3 systems together to form the major body of your robot. All right. So after that, okay, after the design of your robot system, then we want to judge the performance which could be achieved by the robot designed by you. So therefore, this is very important for us to evaluate the performance of the robot designed by you. Okay, so then in this case, we borrow the criteria from control theory. So in control theory, the way for us to judge the response from any system, okay, are based on the use of these 3 criteria. Criteria number 1, stability. Criteria number 2, response time. Criteria number 3, response accuracy. Okay, so then this example show you typical response from scanner robot. So this is a scanner robot. Now you see this robot has a very short response time, and is very stable and is very accurate. Okay, so then right. So you see, okay, today it is achievable for us to have a very stable robot, very accurate robot, and a very fast robot. But of course, we cannot reduce this one to 0 seconds. Okay, so we just shorten response time. All right. So then I'm going to give you a little bit of detail about the concept of stability. For robotic arm, should be quite straightforward. So when you do pick and place, and we do not want the robotic arm to oscillate at the final position. Okay, so that's for robotic arm. Then how about mobile robot? You may have a view the mobile robot, lag the mobile robot. Okay, then in this case, we must take care of stability, and in particular for biped walking or lack the mobile robot, stability is an issue. It's a very big issue. Okay, for robot to work very stably on all kinds of terrain is a challenge today. Okay, so this is the area for you to do research. Okay, how to achieve human-like stability. Okay, for biped walking, because for human being, our locomotion system is based on the biped walking subsystem, and in general, human beings are very stable, okay, on the normal condition. All right. So then, how to make a future robot to achieve human-like stability? So that is a challenge for today's research. All right. And then this video show you, okay, why today's robot are very weak, okay, in this domain.
Bis hierher haben beide Teams lange Nächte gehabt, wenig Schlaf. Wir sehen in Schwarz Human, in Blau das Now-Team HTWK. Human kommt aus Bremen, HTWK aus Leipzig und beide haben eine Neuigkeit von diesem Jahr umgesetzt. Eigene Trikots. Anstoß hat anscheinend Human. Und neu dieses Jahr ist auch die Detektion des Anpfiffes. Das bringt ein paar Sekunden, in denen man frei agieren kann. Oder frei agieren kann, sollte es das andere Team nicht erkennen. Und das sieht gut aus. Beide Teams haben es erkannt. Zweikampf jetzt in der Mitte. HTWK kann sich im Moment durchsetzen. Jetzt ist der Ball zwischen den Füßen, das darf nicht sein. Freigespielt, die 4 muss jetzt weiter ran. Zwei Bremer Spieler stehen jetzt davor. Versuchter Pass, das hat nicht geklappt.
All right, so you see, it is a challenge for today's robot to reach human-like stability. Okay, so this should be an area of research for you to pursue in future. All right. So then this is just a simple example exercise for you to consider. And okay, what should be the condition for robot to maintain stability or for robot to lose stability? Okay, the answer should be the projection of a center of gravity must be inside the support polygon between the foot and the ground. Okay, as long as the center of projection center of gravity is project inside this support polygon, then this robot is stable. All right, so then for view with the locomotion, there is also the issue of stability. Normally it is not so serious, okay, because in normal situation there's no issue for view with the mobile base to lose the stability. But however, it's always good for you to know the boundary condition at which the vehicle will start to lose the stability. All right, so this is the purpose of this example. Okay, so this vehicle move along the circular path, the radius is equal to 1.5. Then the weight of this robot is given to you, and okay, the center of the body is also given to you. Okay, it's 0.3 meter above the ground. Okay, so basically this shows you the moment arm of the center of gravity of the robot. All right, so and you understand when this robot has a circular velocity. Okay, then if this circular velocity reach a maximum value, then the radial or centrifugal acceleration, okay, will also reach a maximum value. Then behind centrifugal acceleration, there is a centrifugal force. Then this centrifugal force times, okay, the moment arm will produce a torque about in this case it's about the right view at the right edge of the right view. Okay, when this rotating torque is greater than the counter torque due to gravitational force acting on the body, of the robot, then the body of the robot will start to rotate about the right edge of the right view. All right. So assume this mobile base move in a counterclockwise rotation, whether it's mentioned here or not. Okay. So assume this move in the counterclockwise rotation, then centrifugal force will make this robot to rotate, okay, towards the right-hand side of this mobile base. All right. So the condition should be in order to maintain the stability, so there's a boundary condition. So that means centrifugal force times moment arm. Okay. Then this torque should be smaller than the torque due to gravitational force. So mg times the moment arm. So this is the distance between mg and the right edge of the right view. Okay, because the distance between left view, right view is 0.5 meter. Then half of this value basically is equal to the moment arm of mg. Okay. So then what is centrifugal force? Centrifugal force equal to mass times centrifugal acceleration, which is proportional to circular velocity square divided by radian of rotation. So this condition must fulfill in order to keep the stability of this mobile base. Okay, so you cancel the m, then you know that the circular velocity should not exceed this value. Otherwise, this mobile base will lose the stability. All right. Okay. So this just for you to know. Then what is the response time and how to achieve a very fast response? Okay. So basically, so you see the time taken from the robot to move to the next position. Okay. So this gives you an idea. Okay. So we must make this time as short as possible. All right. Then here is an example for you to calculate. For example, if let's say we want to move this prismatic joint. Okay, so this is a typical example of a prismatic joint. Okay, so then this is the link. The second link is attached here. Then assume this is the second link. Then you can move linearly along this z-axis. So you remember we always use the z-axis to represent axis of rotation or axis of a linear motion. Okay, so okay, then in this case, this question tells you the maximum acceleration which could be achieved by this joint is 5.0 meter per second square. Okay, now we want to let this link to travel 20 centimeter within the shortest time. So what will be the shortest time duration? Okay. So actually we can calculate in theory, all right? So this is the typical example of trajectory planning, okay? So let me do a little bit analysis about the question. So let's say we assign the coordinate system in this way. So when the link is at 0 position, then the z coordinate equal to 0. The maximum acceleration is 5 centimeter per second square. Travel distance 20 centimeter, and we want to make this one as short as possible. Okay, then what should be the equation of a trajectory for this robot to achieve this type of response? Okay, so then we need to design a trajectory for the robot. All right. So. And here we choose the solution with a two phase. That means a trajectory with a two phase, because we want to know what is the shortest traveling time. So therefore, then we just have a speed up phase immediately followed by slow down phase. For speed up phase, we use the maximum acceleration. For slow down phase, we also use a maximum deceleration. Okay, then assume the time taken by this robot is equal to t, because we want to determine t. Therefore, for first phase, the time interval is from 0 to t over 2, and the second phase, the time interval is from half t to t. All right, so these are the key information, okay, from the question. And as a designer, you can choose this design solution. So basically, to come out the trajectory with 2 phases instead of 3 phases. All right, okay. Then for phase 1, we can write down the displacement of the equation for z coordinate. Okay, because this is a constant acceleration and the initial position is here, then the increment of position is proportional to a. Okay, so 1/2 at squared. Okay, then for velocity, so velocity will linearly increase. Okay, initial velocity is 0, then increment of a velocity equal to acceleration times t, so equal to acceleration times t. Okay, so this is for phase 1. Then boundary condition for phase 2 should be when t equal to half of capital T and the t equal to half of the capital T. Therefore, the initial velocity for second phase is equal to this one, and the initial position for the second phase equal to this one. Okay, then for second phase, it is a constant deceleration. So therefore, the increment in the coordinate is equal to the sum of the 2 terms. First term is the increment of a coordinate due to initial velocity, and the second term is the increment of a coordinate due to constant acceleration. So then you have this equation, all right? So then we can apply this condition, okay? So first, we try to come out the time function for z coordinate in phase 2, okay? Because we know this one, so we substitute this one with this initial condition, substitute this one with the initial condition of the velocity. Then we have this equation. Then we use this condition when t equal to capital T, the travel distance equal to 20 centimeter, okay? Because when t equal to capital T, this one equal to 20 centimeter, so it means 0.2. Therefore, we have a single equation with a single unknown. This is a capital T. Then from here, then we know t squared equal to 0.8 divided by 5. Then t equal to 0.4 seconds. Okay, so this is the shortest traveling time, which is achievable by this prismatic joint. All right, so this is a typical example for you to know response time limit. Okay, so this is the limit. You cannot go beyond or make it smaller than 0.4. Okay, so response time must be at least 0.4 seconds. All right. Then response accuracy. So it means when you rotate 5 degrees, there must be 5 degrees. Okay. And if inside your robot's body, there are some error for whatever reason or due to the sensory feedback, etc., then we must do some estimation. Okay. So this video shows you a robot with a very poor accuracy in motion control. So you see, it's very shaky. All right. So then you can start to think how to improve the accuracy of robot's motion. All right. So you can start to think. Then I use this example to help you to understand. Okay, the accuracy at the robot's hand depends on the accuracy at the robot's joint. Okay, if there are error at the joint, then there will be error at the robot's hand. Okay, for example, we just look at the accuracy of a y coordinate. So then in this case, we do not consider z, do not consider x. So accuracy of a y coordinate basically depends on the angular position of a link 1, link 2, because it will not depends on the prismatic motion by link 3. Okay, so only link 1, link 2 involved in the calculation of accuracy of a y coordinate. Okay, and this example shows you the assignment of a coordinate system to the link. So you will see every link has 2 location or 2 extremity. So this extremity is very close to the base, and another extremity is far away from the base. So we call this one is a distal extremity. This one is proximal extremity. Proximal means is in proximity of the base link. Okay, so then you will see the convention in robotics is to assign a coordinate system at the distal extremity of the link, and then use this coordinate system to represent link 1. Then you see link 2. Link 2's coordinate system is here. Okay, so then this is the coordinate system belong to the base link. All right, so then you see the joint 1 basically is placed at the base link. Joint 2 is placed at the link 1. All right, so joint 1 basically will drive link 1. Joint 2 will drive link 2, because when you rotate joint 1, then link 1 will rotate together with joint 1. So try to pay attention this relationship. Okay, so you should not call this as a joint 1. So at the coordinate system of link 1, you will see joint 2, because joint 2 is to drive link 2. Joint 2 is not to drive link 1. All right, so therefore joint 2 is inside the coordinate system of link 1. All right, so there's an offset of a membrane. Okay, so if this is a link 1, then this is a joint 2. All right, okay, so you can consider base link as a link 0. This is link 0, then this is a joint 1. This is link 1, then it's a joint 2. All right, so you consider them in this way. Okay, so this is just a background knowledge for you to know, but anyway, we will come back to this one in lecture 3. All right, okay. Then, okay, for this example, if let's say there is an error, okay, in joint 1, joint 2, then what should be the error, okay, for the y-axis of a robot's hand, all right, okay. So then we do a little bit of analysis of the question, then we withdraw it, because we only want to study the accuracy of a y coordinate. So therefore, y coordinate only depends on link 1, link 2, and the angular position of a joint 1, joint 2. All right, so then we have this setup. Okay, then in the general configuration, θ1 is orientation of a link 1 with respect to the base link, and the θ2 is the orientation of a link 2 with respect to link 1. So this is also another background knowledge for you to pay attention. Okay, so θ2 is not the orientation of a link 2 with respect to the reference coordinate system. Okay, so because this is a kinematic chain, so link 2 is inside link 1, the link 3 is inside link 2. Okay, this is the way to form the mechanism. So therefore, orientation of link 2 is referenced to orientation of link 1. Okay, so beta 2 basically is orientation of link 2 with respect to the link 1. All right, so but for the calculation of error at the robot's hand, then we want to know what is orientation of a link 2 with the same global coordinate system. All right, the answer will be θ1 plus θ2. All right, so θ1 plus θ2 give us the absolute orientation of link 2 with respect to the world coordinate system. Okay, now we should be ready to determine what is the y coordinate. This is the displacement along y-axis. So you will see link 1 will contribute to this y coordinate. Link 2 will also contribute to the y coordinate. And the result is the sum of these two. So contribution to y coordinate by link 1 is equal to L1 times cosine θ1. Contribution to y coordinate by link 2 should be equal to link length L2 times cosine θ1 plus θ2. All right. Then from this relationship, then we can compute the relationship among the variation of y θ1, θ2. Okay, so we just compute first order derivatives with respect to time. So then this is a velocity relationship, and here we can consider dy as a theta y approximatively. Let's say the dt become a theta t. Then this become an error within the time interval theta t. Then theta t, theta t, theta t can cancel out. Therefore, we cancel out the theta t, theta t, theta t, theta t. Then we have this relationship among the variation of a y coordinate, variation of a theta 1, variation of a theta 1, variation of a theta 2. All right. So then this we have this variation equation. Then we consider the worst case scenario. Worst case scenario means what? What should be the maximum error here? So then for sine function, the maximum value is what? 1. Sine function, maximum value is what? 1. Then for theta 1, what is the maximum variation? So this will be given to you by the question. Ideally, we want this to be 0. Okay, if it's not 0, then you put in the value. And the maximum value for this one, okay, is given to you by the question. Maximum variation of theta 2 is also given to you by the question. All right. So therefore, then we have this calculation. Okay, because this is 0.01, this is 0.02, add them together is 0.03. Okay, so this is just simple calculation. Then you see this is the worst case scenario for the variation to be observed at the y coordinate. Then this value is 0.018 centimeter, but actually it's quite smaller. All right, so that's about the accuracy. So now you have a good understanding about these three criteria for us to judge the response from the robot designed by you. Now we zoom into the detail of designing the robot. For example, designing robots mechanic system, designing robots control system, designing robots programming system. Okay, so and before we look at the detail, then you know if we are going to design robot as a product, so then we must follow the common practice or common procedure. So this slide basically show you the flow of a thinking as a designer. Okay, first, as a designer, you must know who are the user of your robot and what are the needs of this user, why they want to use your robot. Okay, then you offer your robot as a product to satisfy the need of this user. Then you want to justify how come your robot could meet the need of your user. Answer is what? Your robot has a functionality. Then for each functionality, you must come out the design specification in terms of performance, stability, response time, response accuracy, etc. Okay, so based on the design specification, then you must come out the possible design solution for each functionality. Then you have a morphologic chart. From there, then you can choose a combination among all the possible solutions. Then the result will be conceptual design. Okay, so among all the possible conceptual design, then you choose the best one you want to pursue. Okay, so once you know what is your conceptual design, so conceptual design basically is a combination of the best solution for each functionality. Then you want to put them together, integrate them together. Okay, so once you have chosen the best conceptual design, then you can start to enter the embodiment design. Therefore, you need to choose to select the material for you to fabricate the link, the mechanism, etc. And also to choose a component device from the market. Try not to reinvent the wheel. All right. So if you have a standard component, standard item, just purchase. Okay. Then you once you purchase the standard item, standard part, etc., you must draw the virtual model. It's like a digital twin. If let's say you buy a motor, you buy a sensor, you buy a power supply, buy a battery, whatever, and it's good to use this keyword, digital twin. Your vendor may not sell the digital twin of a motor, digital twin of a sensor, digital twin of even embedded computer to you. Then as a designer of a mechanic system, you must draw, design the digital twin of all the component, all the device. Therefore, then you can incorporate all these digital twin together to form the digital twin of your robot. Okay, so at this stage, actually you have, as a designer of your robot as a product, you have a digital twin of the physical robot to be produced by you. Then prototyping is what? To fabricate the physical robot of a digital twin. Okay, the physical one from the digital twin designed by you. Then you do the testing to find out whether there's an area for improvement or not, etc. If yes, then you do the improvement. So this we call it as an optimization process. Okay, so after a few rounds of optimization, then eventually, then you may say, oh, my product, my robot is perfect. Then you can go for mass production. Then you can also form a marketing and a sales team to start to find the potential buyer to your robot. All right, so these are the procedure for you to follow. Okay, then what should be the key consideration when you enter into the design of a mechanic system, control system, programming system, etc. Okay, so for mechanic system design, these are the key consideration of appearance design, mechanism design, structure design. For industrial robot, okay, appearance is not important. Okay, so you just focus on mechanism and the structure. For service robot, appearance is extremely important. Okay, so you should start with appearance design. Then this will provide space constraint for mechanism, for structure. Okay, so for industrial robot, you can start with the mechanism design, okay, followed by structure. Appearance is not important at all, okay, for industrial robot, right? So these are the key consideration. Then for control system design, the key consideration should be these three key components inside the control system. Input device means what? Should be the sensor, okay? The sensor or other input device. So primary, it means a sensor, all right? Output device means what? It should be primary means actuator. It can output motion, and the plus other output device, such as the output information of the display. And the input here, the primary device should be sensor, sensory input. And this also includes a keypad for human user to input information to your robot, etc. Okay. Then control device basically means a microcontroller with the input-output module, etc. So these are the key consideration. Okay. And among these key considerations, the primary item should be this one. As long as you have a very good controller, the good brand for your robot, then this controller can easily interface with the sensor, with the other input device, easily interface with motor, actuator, and the other output device, such as a display. Okay, something like that. Then for programming system, design of a programming system. So the key consideration will be operating system, programming language, and user graphic interface. This is to support human-robot interaction. All right. So normally we just choose operating system from the offer in the market. Choose programming language from the offer in the market. Then your focus should be on the design of GUI, and this one is dictated by the intended mode or way of achieving human-robot interaction, whether at the signal level or at the cognitive level, etc. So that depends on the specific application. All right, so these are the key consideration. And the good news is you do not need to design operating system. You do not need to design programming language because there are plenty candidates for you to choose from the market. So then you focus your attention here. Okay, how to facilitate human-robot interaction. The human may mean yourself. How will you interact with your own robot, or how will your user interact with your robot? So you must think in this way. All right. So that's all for this lecture one. So key takeaway from lecture one is for you to know, okay, what to design when you will be in charge, okay, of the task of designing robot as a product. So by now you should understand the three key systems for you to focus on, include mechanic system of the robot, control system of the robot, and the programming system of the robot. So actually module one basically tell you the knowledge about the library function to be implemented, okay, inside the programming system. So that is a learning outcome from module 1. So then you should know, okay, how to implement the software system for your robot. Then the learning outcome from module 2 should be focused on the design of a mechanic system or the physical body of your robot. Then how to design control system. So that will be the focus of the study in module 4. All right. So this lecture gives you overview about the objective of a study in module 2 and the objective of study in module 1. Okay, how to make use of module 1's knowledge to implement the programming language, and also prepare you to study module 4. So module 4 will be focused on the design of a robot control system. All right, thank you for your attention. So I'm looking forward to seeing you in the study of lecture 2